All right, so we're finally here. We've made it to integration chapter 4. Right, I'm just hanging out with my buddy the Iron Man here, and we're going to go over some of the basic rules for integration. So I'm going to open up the PowerPoint. I'll share the PowerPoint with you and go through some of the rules as well as some of the examples. If you have the PowerPoint printed off and you want to follow along with the examples, that might not be a bad idea. So if we take a look at the PowerPoint, it starts off with what is an antiderivative, right? We've been focused on derivatives so long, well, there has to be a process to undo it and go backwards. That's the antiderivative. So an antiderivative is a function f, and that f is now capitalized. So capital F is an antiderivative of the function for every x in the domain. So if you take the derivative of an antiderivative, it cancels out and gets you back to the original function. So capital F prime of x, the derivative of the integral, would cancel out and get you back to the regular function f of x. So this is what it's saying down here, right? If you have an integral, this is the integration symbol here, an integral of a function and you take the derivative, they cross each other out for opposite functions, just like any other opposite functions, and you'll get back to the original function f of x. So when you have an integral, you have several parts, right? Like I said before, the integration is denoted by this integral symbol. So here's your integral symbol. What's inside the integral, like this f of x, is called the integrand. It's what you're taking the antiderivative of. Dx is always placed after an integral if you're using the variable x, because that's your variable of integration. So if your function was in terms of y, you would use dy. If it was in terms of t, you would use dt. Whatever that variable is, it's the variable of integration. For the basic examples we're going to do, they're going to stick mostly with x. After you take the antiderivative of this function, it becomes a new function, and they call it capital F, like I explained before. And there's also this plus c on the end. That's called the constant of integration. Now, why do they need a constant of integration on the end? Well, because when you take the antiderivative of a function, we can't get the exact function without some sort of initial condition. The reason that is if you take the derivative of 2x, right, you get 2. If you take the derivative of 2x plus 2, you still get 2. So there's several functions, right? If you take the derivative, you get the same answer. So when you're going the opposite way, we're not going to be able to get that constant back, so we're going to represent it with a plus c at the end. So every indefinite integral will have a plus c at the end, right? So every integral that looks like this will always have a plus c. Don't forget your plus c. And later on this week, we'll be looking at initial conditions. Can they tell us other information that we can find that constant of integration at? Here are the first 5 rules of integration. If you take the integral of 0 dx, it is just a constant because the derivative of a constant is 0, right? The antiderivative of 0 is going to be a constant. The integral of k dx is kx plus c, right? So if the derivative of kx would be k, the antiderivative of k would be kx, and as always, we put that plus c at the end. The third property or formula here says that if you have a constant in front of a function, so like k times f of x, you can take that constant out, take the integral or antiderivative of the function, and then multiply the constant back through. Number 4 says that if you have 2 separate functions added or subtracted together, you can separate those functions out, take the antiderivative or the integral, and then add or subtract them back together. So you can separate it into pieces, treat it in smaller pieces, just like you could with a derivative, and then combine them back together when you're done. Number 5 is kind of like our power rule, just doing the opposite. So when we took the derivative, we brought the number down front, multiplied it, and then subtracted 1 from the exponent. Now, because we're going the opposite direction, instead of multiplying, you're going to divide, and instead of subtracting 1, you're going to add 1. And instead of bringing it down first, you're now going to bring it down after. So for this one, you're going to take your exponent, you're going to add 1 to it, take the new exponent, and divide by whatever that value is. And then, as always, you put that plus c at the end for that constant of integration. So the exact opposite of your power rule for taking the derivative is the rule for your antiderivative. You add 1. After you add 1, you take that and you divide by that number. All right, so let's go ahead and look at some examples. So the examples, I'm going to switch over here to the document camera and I'll do them with you. Like I said, if you have the PowerPoint, it might be a little easier to just write them down on the PowerPoint as we go along. The first one is going to be something as simple as if we have this constant like 5, we're taking the integral of 5 dx, what is our answer going to be? So if I have a constant, I'm going to add an x onto it. So the derivative of 5 dx would be 5x plus c. Right, and you can always check your work by taking the derivative. If I take the derivative of 5x, the derivative of 5x is just 5. Right, so the integral or antiderivative, any function that's a constant, you just add an x on and put your constant of integration plus c. The second one, we have the integral of x squared dx. Well, if it's x squared dx, then I'm going to use that kind of reverse power rule. So I'm going to add 1 to the exponent. So I'm going to take my original, I'm going to add 1 to the exponent, and then I'm going to divide that by this new exponent, which was that 2 plus 1. So that's going to give me x to the third over 3. And of course, we'll put our plus c, our constant of integration, at the end. Now, if you want to check it with the derivative again, you would use your power rule, bring this 3 down, they would cross out, subtract 1, and you would get back to x squared. So if you're ever worried about it, take the derivative, you should get back to the original. All right, for this one, we have a rule that says if we have a number multiplied by a function, I can take that number out of the integral and just worry about the function itself. So if I do that, I have just an x squared on the inside, which x squared, I already took the integral right here. X squared, we got x to the third over 3. So that's going to be 2, my constant on the outside, times the integral of x squared, which we already found, is this, plus c. So really that's just 2x to the third over 3 plus c. Right, and I guess I should be writing, these are my antiderivatives. So these are my capital F of x's, right? Same thing up here. This would be capital F of x. All right, and then we come down here to number 4. Number 4, I have 2 pieces to this function. It's 8x squared plus x. So my one rule says that I can separate it out. 8x squared dx plus x dx. And then same thing I did in that last problem, I can pull this 8 out. So it's just x squared dx and x dx. Well, once again, x squared we already found, right? So that's 8 times the integral of x squared, which we did in the last problem, in the last 2 problems. That was x to the third over 3. The derivative of x, well, there's this little imaginary exponent of a 1 here. So if I use my power rule, I would add 1 and then divide by that new exponent. So that's going to be x squared over 2. And then I have to remember the plus c. So my antiderivative, my capital F of x, is going to be 8x to the third over 3 plus x squared over 2 plus my constant of integration, c. Right, so in all of these problems, and the problems that you see in the book, sometimes it helps to rewrite them before you start taking the integral, right? Just like when we did derivatives, sometimes you can rewrite them in a way that makes taking the derivative easier. Same thing with integration. Sometimes you can rewrite it in a way that makes taking the integral a little bit easier. So you'll see that in this next one, right? We have 1 over x to the third. Well, that's much easier if I rewrite it as x to the negative third, just bringing the x to the third to the top, changing the exponent to negative. Right, so now I can use that same kind of power rule that I've been using. I'm going to add 1 and divide by that new exponent. Negative 3 plus 1 is negative 2. So the integral, the antiderivative, is going to be x to the negative second over negative 2 plus c, which I don't like having my exponents negative in my answer, so I'm going to rewrite it, simplify it as negative 1 over 2x squared plus c, right? I just put this negative in the top. It doesn't matter if top or bottom. Negative divided by positive, positive divided by negative is the same. So negative 1 over 2x squared plus c. And same thing with roots as we did with derivatives. When we work with derivatives with roots, we never kept them as roots. We always changed them to rational exponents. Same thing goes here. So instead of working with the square root of x, I'm going to be working with x to the 1/2. And then I can use that same rule I've been using. I'm going to add 1 and divide by whatever that new exponent is. So 1/2 plus 1 give me 3/2. Divide it by that new exponent, 3/2. Well, dividing by fractions like multiplying by the reciprocal. So my antiderivative, I multiply by the reciprocal of this 3/2 is going to be 2x to the 3/2 over 3. And then don't forget, you need your constant of integration plus c. So those are the first 5 kind of rules and properties of basic integration. We'll continue this with several more parts in the future. Thanks for watching, and see you next time.